Today, we will learn how to solve equations involving absolute values, also known as modulus functions. This topic is essential for your IGCSE Additional Mathematics exam because modulus functions appear frequently in both algebra and calculus questions. Mastering these techniques ensures you can handle nonlinear relationships where only the magnitude of a value matters, not its sign. By the end of this lesson, you will be able to solve linear and quadratic modulus equations and identify extraneous solutions. Today, we are going to learn how to solve absolute value equations. To solve a simple modulus equation like the modulus of x plus b equals c, where c is a non-negative constant, we must consider the definition of absolute value. Since the absolute value representing the distance from 0 can come from either a positive or a negative value inside the bars, we split the equation into two separate linear cases. We solve for when the expression inside is exactly c, and when it is negative c. This ensures we capture all possible values of x that satisfy the magnitude required. Let us apply this logic to a concrete example. Solve the modulus of 2x minus 3 equals 5. Following our rule, we set up two linear equations. First, 2x minus 3 equals 5. Adding 3 to both sides gives us 2x equals 8. Dividing by 2, we find our first solution, x equals 4. Now for the second case. 2x minus 3 equals negative 5. Adding 3 to both sides here gives us 2x equals negative 2. Finally, dividing by 2 gives us our second solution, x equals negative 1. Both values are valid because the right-hand side, 5, is a positive constant. Next, we look at equations where the modulus of ax plus b equals another linear expression, cx plus d. This type is more complex because the right-hand side contains a variable. Since a modulus result can never be negative, the solution only exists if cx plus d is greater than or equal to 0. We solve the two cases as before, but we must substitute our answers back into the original equation. If a solution results in a negative value on the right-hand side, we must reject it. These are called extraneous solutions. Let's look at why this happens graphically. Consider the graph of the modulus function y equals absolute value of x plus 2 and the line y equals 2x minus 1. Notice they only intersect at one point x equals 3. The algebraic method also finds an intersection at x equals negative 1/3, but there, the line is negative. Let's solve the modulus of x plus 2 equals 2x minus 1. We begin by splitting this into two cases. In the first case, we remove the modulus bars directly. By subtracting x from both sides and adding 1, we get x equals 3. In the second case, we set x plus 2 equal to the negative of the right-hand side. Expanding the bracket gives x plus 2 equals negative 2x plus 1. Adding 2x and subtracting 2 gives 3x equals negative 1. So x equals negative 1/3. Now, we must check for extraneous solutions. If we plug negative 1/3 into the right-hand side, 2x minus 1, we get negative 5/3. Because a modulus cannot equal a negative number, we reject x equals negative 1/3. Our only valid solution is x equals 3. Let's look at an example to understand extraneous solutions. To understand why we rejected that solution, let's look at the graph. The V-shaped graph represents y equals the modulus of x plus 2. The straight line represents y equals 2x minus 1. Notice that the line and the V-shape intersect at the point 3, 5. This corresponds to our valid solution, x equals 3. The second intersection point occurs at x equals negative 1/3. However, this happens below the x-axis where the y value is negative 5/3. Since the modulus function, y equals the modulus of x plus 2 is never negative, it cannot equal the line at this depth. The algebraic method finds where the line would meet the reflected part of the v if it continued downward. This is why we must always verify our answers algebraically. Now, let's look at the next concept. Now, consider the case where we have a modulus on both sides of the equation. One highly effective method is to square both sides. Since squaring any real number results in a non-negative value, the modulus bars are essentially neutralized. This transforms the problem into a quadratic equation. Alternatively, you can treat it like our previous linear examples. Since the magnitudes are equal, the expressions inside must either be exactly the same or have opposite signs. Both methods are valid for the IGCSE syllabus, but method 2 is often faster during an exam. Let us solve the equation. The modulus of 3x minus 1 equals the modulus of x plus 5. We will use the linear cases method. For our first case, we set the expressions inside the modulus equal to each other. Subtracting x and adding 1 gives 2x equals 6. Dividing by 2, we find x equals 3. For our second case, we set the left side equal to the negative of the right side. Expanding the brackets, we have 3x minus 1 equals negative x minus 5. Adding x to both sides and adding 1 gives 4x equals negative 4. So, x equals negative 1. In this specific type of equation, where both sides are enclosed in modulus signs, we typically do not need to worry about extraneous solutions, as both sides are guaranteed to be non-negative. Today we look at the concept of solving modulus equations involving quadratic expressions. The final type of equation involves a quadratic expression inside the modulus. To visualize this, imagine a standard parabola. Any part of the curve that would normally fall below the x-axis is reflected upwards, creating a characteristic W shape for quadratics with two roots. To solve algebraically, we again split the equation into two cases. We set the quadratic expression equal to positive d and negative d. Because we are dealing with a quadratic, each case could potentially yield two solutions, meaning we can have up to 4 distinct solutions for x. Let us solve the modulus of x squared minus 4 equals 3. This equation describes where the horizontal line y equals 3 intersects our reflected quadratic curve. First, we set the quadratic expression to positive 3. Adding 4 to both sides gives x squared equals 7. By taking the square root, we find two solutions. X equals plus or minus the square root of 7. Now, we set the quadratic expression to negative 3. Adding 4 to both sides here gives x squared equals 1. Taking the square root gives us two more solutions. X equals plus or minus 1. Looking at the graph, the line y equals 3 crosses the curve at 4 distinct points. These correspond to our 4 algebraic solutions. Note that the original vertex of the parabola was at negative 4, but the modulus has reflected it up to positive 4. Let us work through a typical Cambridge exam question. First, we solve for the positive case. Adding 10 to both sides gives x squared equals 16. Taking the square root, we obtain x equals 4 and x equals negative 4. Next, we solve for the negative case. Adding 10 to both sides gives x squared equals 4. Taking the square root gives x equals 2 and x equals negative 2. All 4 values are valid solutions. In an exam, ensure you list all 4 distinct values to gain full marks. Missing the negative square roots is a common way to lose marks. Let's look at some common mistakes students often make. The most frequent error is solving only the positive case, such as x plus 2 equals 5, and neglecting the negative case. Remember, the modulus operation hides the original sign, so you must always account for both possibilities. When an equation has a variable on the right-hand side, like the modulus of x plus b equals cx plus d, you might find solutions that make the right-hand side negative. Since a modulus cannot equal a negative number, these must be rejected. Always substitute back to verify. While squaring both sides is a valid method for equations with a modulus on both sides, students often make algebraic errors when expanding brackets, such as thinking a plus b squared equals a squared plus b squared. Always expand carefully using the FOIL method or the binomial expansion. When solving quadratic modulus equations, like x squared equals 7, Many students forget that x can be positive or negative root 7. In a modulus question, this could result in missing half of your required solutions. When you are in the exam, pay close attention to the number of marks awarded for a modulus question. If a question is worth 4 marks, it is a strong hint that there are multiple solutions to find, likely requiring you to split the equation into cases or solve a quadratic. Always sketch a quick graph if you are unsure about the number of solutions. A V-shape or a W-shape intersection with a horizontal line can quickly show you how many answers you should be looking for algebraically. Check the range or domain specified in the question. Sometimes, the exam will state that x must be greater than 0. In that case, even if your algebra is correct, you must exclude any negative values from your final answer to avoid losing marks. Finally, keep your work organized. Label case 1 and case 2 clearly. This not only helps the examiner follow your logic, but also prevents you from getting confused during the algebraic manipulation. It is time to test your understanding. Please pause the video now and attempt these 3 practice questions. Once you are finished, resume the video to see the full step-by-step solutions. Question 1. Solve the modulus of 3x plus 2 equals 11. Question 2. Solve the modulus of 2x minus 5 equals x plus 1. Be careful to check for extraneous solutions. Question 3. Solve the modulus of x squared minus 9 equals 7. Take your time and apply the methods we discussed. Let's go through the solutions. For the first question, we split into 2 cases. In case 1, 3x plus 2 equals 11, which simplifies to 3x equals 9, giving us x equals 3. In case 2, 3x plus 2 equals negative 11. Subtracting 2 gives 3x equals negative 13, so x equals negative 13 over 3. For the second question, we must check our answers. Case 1 gives 2x minus 5 equals x plus 1. Subtracting x and adding 5 gives x equals 6. Checking this, 2 times 6 minus 5 is 7, and 6 plus 1 is 7. This is valid. Case 2 gives 2x minus 5 equals negative x minus 1. Adding x and adding 5 gives 3x equals 4, so x equals 4/3. Checking this, the right side is 4/3 plus 1, which is 7/3. This is positive, so this solution is also valid. For the final question, case 1 gives x squared minus 9 equals 7, so x squared equals 16, giving x equals plus or minus 4. Case 2 gives x squared minus 9 equals negative 7, so x squared equals 2, giving x equals plus or minus the square root of 2. To summarize what we have covered today, always begin by splitting a modulus equation into 2 separate algebraic cases to ensure you find all possible solutions. Whenever you have a variable outside the modulus, you must substitute your results back into the original equation to verify they are valid. Remember that the modulus of a quadratic function reflects any negative portions of the parabola above the x-axis, which can lead to up to 4 intersection points. In the Cambridge exam, show your step-by-step splitting of cases and clearly state your final rejected or accepted values to secure full method marks.